Now we're going to look at the statistical inference technique called hypothesis testing. And first, we'll just introduce it in this video in the context of an actual Supreme Court case from the 1960s. So where does this fit into our data science life cycle? We are now in the corner of the life cycle where we're interested in trying to understand the world by using our data for prediction and inference. So in particular, we're interested in answering questions like, what does the data say about the world? Does it answer our questions of interest? And how robust are our conclusions? What can we trust from the predictions? This is a reminder of the overall context of data science in general. Not only do we want to understand the world better, but ideally, we want to help make the world better as data scientists. And so we're going to see today through this case study that some of these statistical techniques can actually be used to help expose injustice. And thus, ideally, we hope they can be used to help counter injustice as well. So, just based on the skills you've learned so far in the course, we want you to realize you're already empowered to do this, and we'll show you that through this case study. So let me give you a little bit of background. The U.S. Constitution grants what's called equal protection under the law. So anyone who is accused of breaking the law has the right to what is called the due process. We're going to study a Supreme Court case from the 1960s in which a Black defendant was denied his constitutional right to a fair jury. The court ended up making incorrect and biased judgments about the data in the case, as well as the legal processes in the original trial. We will discuss the errors and the bias in the court's judgment, and I will point out that fortunately this case became the foundation of significant reform, and eventually it was overturned, not until the late 80s, but just leave you with that happy thought before we dive in to some of the incorrect original assessments. So, in terms of selecting a jury, under the U.S. Constitution, defendants have the right to a speedy and public trial by an impartial jury. So to try to create that impartial jury, there's a process by which, out of all eligible jurors in a county, what's called a jury panel is selected. And so this is oftentimes people will say, oh, I got called to jury duty. The first few days of that process, they will start weeding out people from the jury panel to decide who's going to make up the final jury. So this first process of getting the jury panel is supposed to provide a representative selection of the eligible jurors. Then the next process that happens is more of a deliberate inclusion or exclusion, where lawyers on both sides of the case can decide who they want to keep or not keep for the final jury. Robert Swain was convicted in Alabama, and at the time, the eligible jurors in the county were 26% Black people. It turns out that out of the 100 people on the jury panel, only 8 of those people were Black people. And then after the process of deliberate inclusion or exclusion, there were 0 Black people on the final jury. So he appealed his case after he was convicted to the U.S. Supreme Court with the reason that there was unfair jury selection in the county's trials. The court denied Robert's appeal, and they claimed that while, yes, there were 26% eligible jurors who were Black in the county, only getting a jury panel of 8% people who were Black was not necessarily a huge disparity. They actually wrote, the overall percentage disparity has been small. So they did not find that to be grounds to support that there was any type of unfairness, at least in the jury panel selection. This is the part that we're actually going to look at as this first step in the process. His appeal also did have some claims about the second step in the process, where those 8 of those 100 people on the jury panel were eliminated and none of them were chosen for the final jury. But that's not the part that we're going to look at because that part doesn't involve randomness. That has a lot more deliberate inclusion or exclusion happening. What we can look at statistically is this first part, in which if we randomly select people from our eligible jurors, could we reasonably expect to see a jury panel that had 8 out of 100 people who were Black? So the court's view is, yeah, sure, 8% is less than 26%, but not that big of a difference to show that there was some type of systematic bias. And our statistical question, is this 8% an actual realistic outcome if the jury panel selection process were truly unbiased? And this is something we can answer with our tools. So we're going to do this in the framework of testing hypotheses. This is a formal framework that is available for statisticians and data scientists, in which you are trying to make a decision between two views of usually how data was generated. It doesn't always have to be that piece, so we'll come back to that, but in general, that's how we're going to start. And these views are called hypotheses. This method, I'll point out, only works if you can simulate data or theoretically calculate distributions under one of the hypotheses. So the null hypothesis is basically your default assumption. It's a well-defined chance model about how the data was generated. And you need to be able to simulate data under the assumptions of this model. We'll call it simulating under the null hypothesis. So you have to set it up in a way such that it's something that you could either simulate or calculate directly. The alternative hypothesis is a different view about the origin of the data. So let's make this more concrete. In the example of the Robert Swain jury selection, here is a possible null hypothesis we could start with. The people on the jury panels were selected at random from the eligible population, which consisted of 26% Black people. Any difference we see between the population demographics and the jury panel is just due to chance, because we were randomly selecting a subset of people. The alternative is going to say no. Not only was this null hypothesis incorrect, but it's incorrect in a specific direction. So we're going to say no, the selection was actually biased against Black people. This is not your only option. You're allowed to set up your alternative so that it specifies a direction, or it may just say no, the null is not true. But in this case, we're going to also specify a direction. Okay, so now the next step in the process to be able to really test this hypothesis is we have to come up with what's called a test statistic. And I'm going to do it via an example here first, and then we'll generalize this. A possible test statistic we can use in this case is the number of Black people chosen out of 100, assuming the null hypothesis. Okay, so notice what this means. I need to choose a test statistic where I can then either simulate or directly calculate the distribution of that test statistic under the null hypothesis. And so we can actually simulate this number of Black people chosen out of 100, assuming our eligible population has 26% people who are Black. In fact, I want you to think about what types of models or random variables we've used in the past that would actually be a great model for this test statistic. Okay, so if you realize there's two ways you can think of this, we can think of randomly sampling from a Bernoulli distribution where the probability of being a Black person is 26%, the probability of not being Black is 1 minus 26%, and we can imagine repeatedly sampling from a Bernoulli distribution 100 times, where these random variables or our sample points are independent and identically distributed. If that's what we do, then the number of people out of 100 who are Black in that simulation is actually well modeled by a binomial distribution. So this is a great, reasonable way to model the distribution of our test statistic. It is assuming that we're doing basically a random sample with replacement when we are selecting the jury panels. And I'm not sure if that was the process at the time, but we can say even if they weren't doing with replacement, if they were doing a random sample without replacement, because we were sampling a total of 100 people, it's definitely going to hit the 10% rule. That's definitely less than 10% of the entire population in that county. So either way, we're okay with this assumption that the samples are IID. And so we're going to stick with this binomial model as a good way of modeling the test statistic under the null hypothesis. And so here's the distribution of the test statistic under the null. So notice, this is a prediction about the statistic made, assuming, right, the null hypothesis is true. It's showing all the likely values of the statistic and how likely they are, right? This is the probability mass function for the binomial distribution. All right, and then to show you, we can plot this from Python. I'll go to that in just a minute because I have this in a notebook, but this is something that we have done before when we were doing the binomial distribution. Okay, now once you have that distribution of your test statistic, you're going to then see where your observed test statistic appears on that distribution. In our case, the observed test statistic was 8 because there were actually 8 out of the 100 people on the jury panel that were black. And so you can see that this is in the far tail of the distribution. In fact, it's highly unlikely. The probability of 8 had to be so small I can barely even see it on here, right? That's nearly impossible to see. What we're looking for as part of our hypothesis test is where that observed test statistic is. And the convention is if it's in the tail of the null distribution, which this one is, and we're going to talk a little bit more about how we define the tail, then we can reject the null hypothesis, meaning that the data that we've collected makes our null hypothesis look pretty ridiculous. The data is more consistent with the alternative. Now, this in the tail is going to be important. We're going to quantify that in particular by calculating a specific probability. We're going to calculate, given the null hypothesis, so that's the distribution we're working with, the probability of the observed test statistic or something more extreme, meaning something more in the direction of the alternative. So our direction of the alternative is saying biased against black people. So I'm really going to want to get the probability that X is less than or equal to 8. Now I'm putting it down here. There's you can't even see it on this plot. It's such a tiny number, which is making my null look ridiculous. Like the probability of seeing this result is very unlikely if this were the true null distribution. So let's calculate it. Probability X is less than or equal to 8 is teensy tiny number. All right, and that's an important number that we use in this hypothesis test process. This number has a name, and we will be diving into this in much more detail in the next video, but this is actually called the p-value. For our purposes, we're just noticing that's a tiny probability and that our observed test statistic is definitely in the tail of our null. So what do we conclude? In this process, we say that our results, our data is inconsistent with the null in the sense that my test statistic is it's in the tail, right? The probability of seeing an 8, given that this was the null distribution, is very small, or given that the null distribution was true. Now, what do I mean by in the tail? Because obviously we could probably all agree that 8 seems pretty extreme, but what if I had gotten something closer to say 18? Would that be enough to seem unusual, or would that be reasonable to expect? And statisticians have come up with some conventions, at least when it comes to these hypothesis tests. The first convention is if the p-value, if the area in the tail is less than 5%, then we say the result is statistically significant. And the second convention is if that area, by the area meaning the area from your observed test statistic and then in the direction more extreme, the direction of the alternative. If that's less than 1%, we say the result is highly statistically significant. So that's what we have in this case. Our conclusion from this hypothesis test is, well, our area in the tail is definitely way less than 1%. And so we then reject the null. Okay. I'll be very careful here. It doesn't mean that we've proven that the alternative is true. You can't, in this process, we can't prove that either one of these is true. All we can do is say which alternative is our data more consistent with. And so our data is more consistent with the alternative hypothesis that the jury selection was biased against Black people. And the result's highly statistically significant because this probability was so teensy tiny. So at the end of the day, we reject the null and say the data is more consistent with the alternative. So we're going to go to hypothesis test here, and then hypothesis testing. And I'm going to add the caveat that in this case, we knew the distribution theoretically, the binomial distribution. I didn't have to do any simulation. But we'll see in next examples, if it's something a little more complicated for your test statistic, you may need to do simulation instead of using built-in random variables, since we've only covered a few of the common random variables. So here I am actually just writing the PMF directly for the binomial out the long way. You could also use the built-in stats.binom, but I'm going to plot it here along with the observed test statistic on our distribution. And then we'll point out, let's actually see where that calculation for the p-value came, the probability of observing 8 or less jurors who are Black. So I can do that two ways. I can just sum the probabilities of 0 up to 8, or I can do stats.binom.cdf. I'm going to get the same answer either way. And that got us that number that we used. Since that was definitely smaller than one of the conventional cutoffs of 0.01, we are able to reject the null hypothesis at the 1% significance level. So this was a pretty straightforward example because our test statistic was directly modeled by a binomial random variable. So our hypothesis test allows us to conclude that we do have quantitative evidence of unfairness in Robert Swain's trial. And the data does support his position that he was denied the impartial jury to which he was entitled. I will point out that arguments such as the one in these previous slides are now more frequently presented in courts of law, but they weren't as common in the 1960s, and so when the Supreme Court looked at the data at the time, they did draw the wrong conclusion. Their meaning of small, quote, it was wrong really to rely on either what simply seemed reasonable to the majority of the court, without looking statistically at what was possible. Because views on what was reasonable were not only purely subjective, but they are also vulnerable to the influence of pervasive racial prejudice. So if arguments in the case had included the quantitative analysis that we did on the previous slides, the court might not have concluded that the percentage disparity was small. Now, I will point out that a hypothesis test does not establish causality. So this alone doesn't tell us what happened and why this jury selection was unfair. To do that, it actually requires looking a little bit deeper into the Supreme Court judgment statement. And Robert Swain actually brought to light, as part of his appeal, the fact that this was not a one-time situation. So he actually looked at jury panels since 1953 and found that the percentage of Black people on those panels was usually 10 to at most 15%. I think there was one case in which the percentage was as high as 23%, but basically they were consistently getting numbers that were super unlikely had the true sample been a random sample from the eligible population. So this was not just a one-time thing, is what he showed. This really happened over multiple years. Now, why was this occurring? Again, if you dive into the Supreme Court judgment, it actually does give us some insight because it tells how the jury panels were selected. And so in the context of our sampling discussion, this is actually telling us what the sampling frame was. The sampling frame came from a jury roll, And these were names that the jury commissioners acquired from city directories, registration lists, club and church lists, conversations with other people in the community, and personal and business acquaintances. So that statement alone is giving us some insight that the sampling frame didn't reflect the target population. And that was leading to the fact that when you took a sample from that jury roll, our jury panel was not representative. So this is an example of where we do have selection bias occurring in the sample, but it's really due to an issue with the sampling frame. I'm unsure if they did then take, a simple random or a random sample with replacement from the jury roll. They might have done that correctly, but the jury roll itself had selection bias issues. Now, I will add that there is a lot of interesting follow-up to this in the link on the previous slide where I sent you for further reading, but it did turn out that this case was overturned. Not until much later. It was reversed in 1986, mainly on grounds about this step here. But regardless, either way, the case did eventually get overturned. We are going to see that unfortunately it's not guaranteed that juries are still free of this problem. In spite of all of this work we've done, racial bias in jury selection still does persist. And we're going to see in another example a more recent case of this in a California county. So this is just an example of how we can use data science to help us expose as well as hopefully address some issues in our systems.